Assalamu alaikum everyone, this is Fahad Ansari and I'm here to help you conquer chemistry. In this video, we will try to cover all of the A2 organic chemistry syllabus within 90 minutes. So without further ado, let's get right into it. So first question asks us for the structure of a benzene molecule. Now benzene molecule, its formula is C6H6. And these carbon atoms are basically spread out in a hexagon. So you have 6 carbon atoms in a hexagon, and the simplest visualization of the bonding in this hexagon is of alternating single and double bonds. So you have alternating single and double bonds. So each carbon atom, as a result, is bonded to one hydrogen atom each. So if I consider this carbon atom, it is bonded to 1, 2, 3 atoms, right? And it has no lone pairs. So around this carbon atom, the shape is going to be trigonal planar. Shape is going to be trigonal planar around each carbon atom, and the bond angle is going to be 120 degrees. It's going to be 120 degrees. So if all of these carbon atoms have a trigonal planar shape about them, that means all of the carbon and hydrogen atoms are in the same plane, right? So in the entirety of the benzene molecule is planar, right? So it is a planar molecule. All right, now these carbon atoms have alternating single and double bonds, and double bonds include pi bonds, which involve the side-on overlap of p orbitals. So if I draw in those p orbitals that are overlapping side-on, one for each carbon atom, so I have an overlap over here in this pi bond, an overlap over here in this pi bond, and over here. Now, these alternating single and double bonds have these p orbitals overlapping in a certain direction, but what is stopping them from overlapping in the other direction? For example, if I talk about this p orbital, it's overlapping this way, but why can't it overlap this way? Well, the answer is it can, and it does. So we show that overlap over here, and over here. And so all of these p orbitals, they overlap and they form a pi bonding ring. So a pi bonding ring is formed, and within each double bond you have 2 electrons in the pi bond, right? And because you have 3 such pi bonds, so you have 6 pi electrons. So 2 pi electrons in this pi bond and 2 more pi electrons in this pi bond. So 6 pi electrons. Now because the p orbitals are overlapping side-on in both directions and forming a pi bonding ring, these 6 pi electrons get to move around throughout the 6 carbon atom ring. So we call this a delocalized pi bonding ring. Delocalized because the pi electrons are free to move. Right. Now, these carbon atoms over here, if I take the example of a carbon atom again, draw this over here, you have a double bond, a single bond, and a single bond, right? So the carbon atom is forming 1, 2, 3 sigma bonds, and it has no lone pairs. So these 2 add up to give you 3 hybrid orbitals, and 3 hybrid orbitals can be obtained from sp2 hybridization. So that's the answer to this part, sp2 hybridization. And because all of these single bonds have a partial double bond character because of the overlap of p orbitals in both directions, so all of these bonds have the same bond length, right? So all of them have the same bond length. And they have the same bond energy as well. Because all of them are essentially single bonds with double bond character. So that's the structure of a benzene molecule. And compounds that contain one or more benzene rings are called arenes. Right, so let's take a look at the reactions of the simplest arene, which is a benzene molecule itself. So it says chlorobenzene can be prepared from benzene as shown, right? And this fellow over here, AlCl3, catalyzes this reaction. Now, when it catalyzes this reaction, it generates what we call an electrophile. And we know that an electrophile is an electron deficient species. And basically what happens is that the AlCl3 catalyst reacts with the other reactant, which is chlorine. It reacts with chlorine and it produces two ions. It produces Acyl positive and AlCl4 negative. This Cl positive over here is your electrophile. Now, the benzene will react with this electrophile in a mechanism that is known as electrophilic substitution. So you've seen reaction mechanisms before in my AS level organic chemistry revision video. If you don't know what I'm talking about, you should watch that video as well. It might help you out. So in electrophilic substitution, you have a benzene molecule. Draw this hexagon, and I'm going to draw this circle to show the pi bonding ring. And we have a chlorine positive ion over here, which is our cation. And we're going to show a curly arrow going from the pi bonding ring, which is electron rich, right? So this is an electron rich or electron dense pi bonding ring. And this attracts an electrophile, which is electron deficient, and it attracts a pair of electrons from the benzene ring. And so what happens is that one of the carbon atoms gets bonded to the hydrogen, which is already bonded to, and the electrophile as well. And the positive charge is obtained by the benzene ring. So the pi bonding system is broken up. It no longer has 6 carbon atoms, but 5 now. It does not include this carbon atom, which is bonded to the electrophile and the hydrogen. So the positive charge of the electrophile gets distributed throughout the delocalized pi bonding ring. Now what happens next is the C8 single bond, it undergoes heterolytic fission. So this over here that I've just shown is heterolytic fission. Both electrons in this bond pair go to the benzene ring to neutralize this positive charge, and so we are left with 2 products. We have chlorobenzene over here, and we have the hydrogen ion. This is the electrophile that was substituted by the new electrophile, which is the chlorine cation. Now, an equation to show how the catalyst is regenerated. Now, for this, the anion that was formed in the first equation over here, this AlCl4 negative, this is going to react with the substituted hydrogen ion. It's going to give us the catalyst that was regenerated, which is AlCl3. And we have HCl, which is the other product in this reaction. So other reactions of arenes involve other substitutions as well. So over here we have methyl benzene. So one of the hydrogens has been replaced by a methyl group over here. Now methyl benzene can undergo further substitution reactions as well. Now for this we need to understand that this methyl group over here is electron donating, right? which means that it will donate this bond pair to the benzene ring, making it even more open to electrophilic attack. And so this activates certain positions in the benzene ring for substitution. So if I number these carbon atoms, the carbon atom bonded to the methyl group, the first substituent is number 1, and this is number 2, number 3, number 4, number 5, and number 6. Now, notice that numbers 2 and 6 are equivalent because they're both one carbon atom away from the carbon bonded to the first substituent, and you could say the same about 3 and 5. They're 2 carbon atoms away each. Right, so this is the numbering. Now, positions 2, 4, and 6 are activated by the electron donating first substituent, right? And so you can see that while the CH3 has been converted into CO2H in compound G, you can see that positions 2 and 4 have been occupied by new substituents. So before converting CH3 into CO2H, we will do the electrophilic substitution reactions. So in the first step, let's say I go with this NO2 substituent, and this comes from nitric acid, and we need sulfuric acid catalyst for this, and a temperature of 25 to 60 degrees Celsius. And so what will happen is that position 1 obviously already has the methyl group, which is CH3. Position 2 is now going to get the nitro group, which is NO2. And in step 2, I will do another substitution. Now position 2 has been taken up, so position 4 is up for grabs. So for that, I'm going to have bromine with AlBr3 catalyst. This is pretty similar to how chlorine reacted with benzene to form chlorobenzene in the previous question. So we have the benzene ring, and we have the methyl group bonded to carbon atom number 1, the nitro group already over here, and a bromine over here. Now notice that bromine has substituted one of the hydrogens in the benzene ring. It is also possible that bromine substitutes one of the hydrogens in this alkyl side chain or substituent. But for this you would need UV light. That would be free radical substitution that you have already seen in your AS level, right? So this is UV light, right? But you do not need UV light for substitution into the benzene ring. You need this catalyst. So there's a difference in the conditions required. Now in step 3, we will convert the CH3 into CO2H, and this is an oxidation of the alkyl substituent. For this, we will need hot alkaline KMNO4. Now the reason why we did not convert the methyl group into a carboxylic acid group in the first instance before the substitution is because CO2H, if I draw this separately over here, CO2H is actually an electron withdrawing group. It's an electron withdrawing group, and so it deactivates the 2, 4, and 6 positions, and it activates positions 3 and 5 instead. And since these will be more open to electrophilic attack in substitution reaction, and the final product does not have these substituents at 3 and 5, but at 2 and 4, because of that, we're not going to convert CH3 to CO2H first. We will do the substitutions followed by oxidation of that alkyl substituent. Now give the systematic name of compound G. Now this is the main arene that has 2 substituents in it. This is actually called benzoic acid. And the carbon atom that is bonded to the carboxylic acid group is number 1. And we can see that benzoic acid has a nitro group at number 2 and bromine at number 4. So we will name this as 2-nitro 4-bromo. These are the two substituents at positions 2 and 4. And then we will follow that up with the name of the base arene, which is benzoic acid. So another question over here, this is another type of reaction. We have benzene reacting with D to give you cumene, right? Now, cumene has this alkyl side chain or substituent over here. And if I draw the structure, this becomes something like this. This is CH3. You have a C, you have a CH3. And this is bonded to it, H. And basically, this alkyl side chain has to be bonded to a chlorine, has to be a chloroalkane, that will be the reactant D. And to name this chloroalkane, we have 3 carbon atoms in this longest carbon chain, right? And carbon atom number 2 is bonded to the chlorine. So we will just name this 2-chloro because carbon atom number 2 has the chlorine atom, and you have 3 carbon atoms, so propane is the name of the main branch. And E over here is going to be obviously HCl, because you're going to get rid of this chlorine over here, and it's going to react with the hydrogen that is removed from benzene to form HCl, so we can write the name as hydrogen chloride. So give the name of the type of aromatic substitution. Now this is a reaction called alkylation, because you're introducing an alkyl group as a substituent, right? And in this case, the electrophile will be the alkyl carbocation, right? Because this CCl bond over here, this will be broken such that the Cl becomes an anion, right? We have an anion over here, and we have the carbocation that I'm going to draw like this. So cumene can react with hot KMnO4. Now for this, what we need is the alkyl side chain has to have a carbon that's directly bonded to the benzene ring that has to have at least 1 hydrogen bonded to it. So in this case, it does. So if this condition is met, this will be completely oxidized to give you benzoic acid. The carbon atom bonded directly to the benzene ring will be converted into a carboxylic acid group, and the rest will be just converted into carbon dioxide and water. And there's only one reaction involving arenes that destroys the pi bonding system, which is normally considered to be very stable. So you need harsh conditions of high temperature and high pressure to destroy this stable pi bonding system. And in the presence of nickel catalyst and hydrogen, this reduction reaction takes place, and the pi bonding ring no longer exists, and it just replaced by this cyclohexane ring. So there are no pi bonds in this at all. So another type of reaction that arenes go through is called acylation, right? Now benzene in step 1 has got this group over here, right? Now any group that involves an R group, an alkyl group bonded to C double bond O, and then the carbonyl group is bonded to something else. It can be anything. It can be hydrogen, it can be chlorine, it can be another alkyl group, whatever. Now this is the functional group of, which is called the acyl group, right? So an acyl group has been introduced as a substitute rather than an alkyl group, so this is actually acylation. And for acylation, what you need is this acyl group, right, which is bonded to chlorine. Just like in alkylation, you needed an alkyl group bonded to chlorine. That's a chloroalkane. In this case, because you have a chlorine bonded to an acyl group, you call this an acyl chloride. We will look at acyl chlorides in much more detail later in the video. All right, so in this case, the acyl chloride has a CH3, C double bond O, Cl. Because it has 2 carbon atoms, so we name this as ethanoyl chloride. So ETH for 2 carbon atoms, and the rest of the name is anoyl chloride. Right, and we need a catalyst for this, and in this case it will be AlCl3 catalyst once again. And once we have this acyl chloride, the next step is to actually reduce the carbonyl group over here, and we will get an alcohol group out of this. Basically, for step 2, this is reduction, and we will need NaBH4 as our reducing agent to convert the C double bond O into CHOH, right? So this is a secondary alcohol group. Now, because we still have a CH3 over here, now this alcohol, this secondary alcohol, can undergo dehydration. This OH is lost alongside the H from the neighboring carbon atom, and so we have a double bond over here, which is shown here. This is dehydration, basically making this guy very thirsty. So, double bond over here, an alkene is formed, and for this you need concentrated H2SO4, or you could use Al2O3 as the catalyst. So this is enough about arenes. We shall inshallah move on to the next topic, which is phenol, another special arene. So phenol is a special arene with a hydroxyl group bonded to the benzene ring in place of one of the hydrogen atoms. So its structure looks something like this. So phenol is a weak acid, and we show this weak acid property using a reversible reaction. It dissociates to give a hydrogen ion, and the anion over here, the conjugate base, we call this the phenoxide ion. So the phenoxide ion has a negatively charged oxygen atom. And the thing about this phenoxide ion is that the oxygen over here, which is negatively charged, has a lone pair in a p orbital. So if I show this p orbital over here, it carries a lone pair, and this overlaps with the pi bonding ring of the benzene, right? And because it overlaps partially with the pi bonding ring of benzene, the lone pair gets delocalized, and so the negative charge on the oxygen atom, its charge density goes down, and so it is less attractive to the hydrogen ions, and so the concentration of the separated hydrogen ions in solution remains high, and so it is the most acidic out of these three substances that we have been given with, and water comes in the middle, and ethanol is actually the least acidic. The reason why is because ethanol has an OH group that is bonded to an electron donating ethyl group, C2H5. This is electron donating. It has a positive inductive effect on the oxygen. So when this dissociates into a hydrogen ion and the anion, which we call the ethoxide ion, C2H5O negative, the negative charge over here becomes more dense or more concentrated due to the electron donating effect of this alkyl group on the negative oxygen. So this negative charge goes up, and so the hydrogen ions are more attracted to this ethoxide ion. This is the ethoxide ion. And because of this greater attraction, the equilibrium shifts to the left-hand side towards the undissociated ethanol molecules, and the concentration of H plus is low, so that means low acidity. So phenol, just like benzene, can undergo electrophilic substitution reactions. For example, it reacts with nitric acid to make this product over here, 2-nitrophenol. Now, this is so named because the carbon atom that is bonded to the OH group over here is number 1, and so this becomes carbon atom number 2, which is bonded to the nitro group. So 2-nitrophenol. And this is because the OH group is also electron donating, so it activates positions 2, 4, and 6 for further electrophilic substitution. Right. And the conditions for the nitration of phenol are slightly different from the conditions for the nitration of benzene, in that you do not need a catalyst, right? So no catalyst needed and no heating required either, right? You just require room temperature and you're ready to go. And in fact, with benzene, you need concentrated nitric acid, but with phenol, you just need even dilute nitric acid will work, right? So you can see that if this reaction can take place with lower concentration of the other reagent, which is nitric acid, and at a lower temperature, and without the need of a catalyst, then that shows us that phenol, in fact, is more reactive than benzene. And the reason why it is more reactive than benzene is, again, if we look at the structure of phenol, we have an oxygen atom bonded to the benzene ring, which carries a lone pair, and that lone pair becomes delocalized into the benzene ring. This lone pair in the p orbital, it overlaps with a p orbital of the carbon atom it is bonded to, which of course is part of the delocalized ring. And so that contributes 2 more pi electrons to the delocalized system, and so that makes it more electron dense or electron rich. And because of that, the benzene ring becomes more open to electrophilic attack. That's why it is more reactive than benzene. So phenol also reacts with aqueous bromine, right? And in this case, it also does not need a catalyst, unlike in the case of benzene, which requires AlBr3, as we saw earlier. So with an excess, what happens is, well, if we just had a small amount or a few drops of aqueous bromine, then the bromine would substitute at either 2, 4, or 6. Either of these 3 positions would get a bromine. But with an excess, this is the key word, excess, we get bromine at position 4 and position 6 as well. So we would name this as 2,4,6 tribromophenol, because the ending of the name is the original arene, which is phenol, and it gets bromine atoms substituting the hydrogens at positions 2, 4, and 6. And that's 3 bromines, so that's tribromophenol. Now observations. Now obviously when the aqueous bromine reacts with something, it becomes decolorized, same as in the case of alkenes. When the double bond reacts with aqueous bromine, it becomes decolorized. And another observation is that this product over here, 2,4,6 tribromophenol, this is going to give off a white precipitate. So that's the second observation that you need to write down. So phenol can also react not only in electrophilic substitution reactions, but also in reactions that just purely involve its OH group. All right, so its OH group over here can react just like alcohols with reactive metals to give us salts and hydrogen. So we have over here potassium phenoxide. Now, if it reacts with pure potassium, then it's going to give us potassium phenoxide. This hydrogen is replaced by the potassium. You get this salt over here. The phenoxide ion has an O negative, then we have K positive. So this is an ionic salt, and you get hydrogen gas as the other product. This is a redox reaction, just like in the case of alcohols reacting with sodium metal. So the substance we will write as simple potassium, and the second product is going to be hydrogen gas. And we could also make it react with potassium hydroxide, right? So if I react this with potassium hydroxide instead, then what will happen is that this H and the OH will form the second product, which is water, right? Otherwise, this reactant and this product will be the same in both cases. So I'm going to write potassium hydroxide. So strong alkalis can also react with phenol to give us a phenoxide salt, and in this case, the second product will be water. So let's get on to some more complicated substances involving phenol, right? So over here we have this part of the molecule, which is phenol, and we also happen to have a benzene ring, and we happen to have this ester linkage over here. So we need to look at which of these functional groups will react with these three reagents. So let's look at it. Sodium over here will react with only the phenol part, right? It will not react with the ester. It will not react with the benzene ring. This is the ester. This is the benzene ring. And this is the phenol functional group. Right. So because it reacts only with the phenol, so what I'm going to do is I have the structure in front of me over here. So what I'm going to do is just going to wipe out this hydrogen over here, and in place of it, I'm just going to write the sodium. This is O negative, Na positive, right? So this reaction is a redox reaction as we have seen before, right? The other product is going to be hydrogen gas. Now bromine over here, now this is aqueous bromine. Now if this were bromine in the presence of AlBr3, then we would also consider benzene, but because this is aqueous bromine without a catalyst, that will only react with the more reactive phenol functional group. So what I will do is I have carbon atom number 1 bonded to the phenol group, and carbon atoms 2, 4, and 6 are activated by the presence of this OH group. Now 6 already has the ester linkage bonded to it and the rest of the molecules, so I'm going to show a Br at carbon atom number 2 and a Br at carbon atom number 4. So that's going to be my structure, and this is an electrophilic substitution reaction that is taking place. Now, with an excess of hot NaOH, now what happens is that two functional groups will react in this case. It will be the phenol group as well, so it will react and it will give us the phenoxide, sodium phenoxide, and this ester over here is going to break down in a reaction known as hydrolysis. This reaction is going to be hydrolysis, right? And this carbon-oxygen single bond over here, this that I'm highlighting right now, this is going to break, and we're going to get two parts of this molecule. So this first part over here on the left, this is going to bond with an OH, and this is going to bond with O negative and a positive, right? This is your sodium phenoxide part, and this OH comes from water. The hydrolysis breakdown by water. And the second part is going to bond with the H from H2O. But wait, this phenol over here that has been formed by hydrolysis, OH part bonding with the C double bond O, at the H bonding with the O in the ester linkage. This forms phenol, and because we still have an excess of hot aqueous NaOH, this phenol can react further with the NaOH to give us, again, sodium phenoxide. So I'm going to, in place of this, I'm going to write Na positive, O negative, right? That's going to give us sodium phenoxide. All right, so that's enough about phenol. Next, we will look at carboxylic acids and acyl chlorides. So in this question, it asks us to explain the relative acidities of 3 carboxylic acids. So we have trichloroethanoic acid, chloroethanoic acid, and ethanoic acid. So let's start with this last acid over here. So we know that weak acids, they partially dissociate to give us hydrogen ions in aqueous solution. That's the case for all carboxylic acids. Now, when we talk about the strength of carboxylic acids, it really depends on the charge distribution on the conjugate base over here. So this is our conjugate base, and the more concentrated the charge is, this negative charge on the oxygen atom of the conjugate base, the more attractive the conjugate base becomes to the H+, and the lower the concentration of H+ in aqueous solution, and the lower the acidity, right? So in this case, for the ethanoate ion, we have a C double bond O, single bond O group over here. Now the thing is that because this carbon over here and this oxygen have a pi bond between them, and this negatively charged oxygen over here carries a lone pair in the p orbital that can overlap completely with this pi bond. So this negative charge becomes delocalized. It becomes delocalized, and so the charge concentration or charge density goes down, and so the concentration remains relatively high of H+, but this is countered by the fact that this CO2 group is bonded to this alkyl group, which is electron donating. So because this is electron donating, so this CO2 negative, its charge density goes back up slightly, and so the concentration of H+ remains slightly on the lower end. So ethanoic acid has a relatively lower acidity or relatively higher pH. But if we talk about chloroethanoic acid, the difference is that this CH3 becomes a CH2Cl, and so this electron donating alkyl group becomes not so electron donating anymore, because it now has this, an electronegative chlorine atom that withdraws electrons away from the CO2 negative group. And so this charge over here, it basically has a lower charge density, and so it is less attractive to the H+, and so its concentration remains high in aqueous solution, and so it has a higher acidity. And if we then replace all the hydrogens with these electronegative chlorine atoms in trichloroethanoic acid, then we will have thrice the electron withdrawing effect in this alkyl group, and so the CO2 negative, its negative charge will be even more distributed, and its density will go even further down, and so the concentration of H+ that remains in solution will be even higher. So in terms of acidity, trichloroethanoic acid is the guy that takes the cake. This is followed by chloroethanoic acid, and at the end, coming in a third, is going to be simple ethanoic acid. So this is the ranking of acidities of these carboxylic acids. Now, carboxylic acids generally do not get oxidized, but there are two exceptions. One is your methanoic acid, which is over here. This is methanoic acid. And there's another acid that undergoes oxidation, and this is this guy over here, two carboxylic acid groups that are bonded to each other. This is basically ethane dioic acid, also known as oxalic acid. So both of these can undergo further oxidation to carbon dioxide and water. Now, the oxidizing agents basically are different for both of these. For methanoic acid, it can undergo oxidation much more easily. So you can use weaker oxidizing agents such as Tollard's reagent or Fehling reagent. The same oxidizing agents that we use for aldehydes. So Tollard's reagent or Fehling's reagent. That will give a positive result with only methanoic acid, not with ethane dioic acid, and certainly not with whatever acid this is. It is not going to be oxidized. Okay, so with Tollard's reagent, we know we're going to have a silver mirror. And with Fehling's reagent, we're going to have a red precipitate. And in both cases, you're going to have effervescence because of the production of CO2 upon the oxidation of methanoic acid. And I'm going to skip to number 3 briefly. And you can see over here that both methanoic and ethane dioic acid are being oxidized. And so that basically means we're going to use a stronger oxidizing agent such as acidified KMNO4, right? And normally with KMNO4, we will need to use some heating as well. By the way, in the experiment number 1, we would also need to use a little bit of heating with Tolland's or Fehling's reagents, right? So with acidified KMNO4 plus heat, both of these will be oxidized, and you will get a color change from purple to colorless. And again, you will have effervescence due to the production of CO2. And in test number 2, neither methanoic nor ethane dioic acid are reacting, which means it's not the CO2H part of this molecule that's reacting. It's this guy over here, right? It's this carbonyl group that is reacting. And because this carbonyl group is essentially telling us that this is a ketone, it's not going to react with Tollard's or Fehling's reagents. It is going to react instead with 2,4-dinitrophenylhydrazine, also known as 2,4-DNPH. And this is going to give us an orange precipitate, right? So that's for these two carboxylic acids that can be further oxidized, but these are the exceptions rather than the rule. So now let's talk about acyl chlorides. We have 3 organochlorine compounds over here. So over here we have chloroethane, simple halogenoalkane, and over here we have chlorobenzene that we have seen before. And this over here in the middle, it has the COCl functional group, which is displayed like C double bond O, single bond Cl. This is your acyl chloride. Now, because it has 2 carbon atoms, so 1 and 2, we're going to call this ethanoyl chloride. Ethanoyl chloride, that's how we name the acyl chlorides. Right, so which of these is going to undergo the fastest hydrolysis? In other words, the reaction with water. So the answer to that is the acyl chloride is going to react the fastest. The reason is that in all of these reactions, the water molecule is going to react as a nucleophile, right? The electronegative oxygen atom carries a lone pair that will attack the partial positive carbon in the organochlorine compound. And in this case, because this carbon over here is bonded to 2 electronegative atoms, oxygen as well as chlorine, that are both electron withdrawing, this partial positive charge is pretty high, and so it will attract the nucleophile, which is the water molecule, more easily, right? And in the case of this acyl chloride, basically what will happen is it will undergo an addition-elimination reaction. This carbon-oxygen pi bond is going to undergo heterolytic fission, and so this is going to result in an intermediate that is overall neutral. So the oxygen over here has a negative charge, and the oxygen over here that donated its lone pair will carry a positive charge. Now what happens is that this negative oxygen donates a lone pair back to the carbon-oxygen bond to reform the pi bond. This carbon-chlorine bond is now going to undergo heterolytic fission, and so is this oxygen-hydrogen bond, such that both electrons go to the oxygen over here, right? And so this is going to result in the formation of a carboxylic acid over here, and you're going to get HCl as the byproduct. So this mechanism over here is the addition-elimination mechanism for acyl chlorides that we have just looked at, right? And acyl chlorides, they undergo this kind of reaction with water, with ammonia, with amines, and with alcohols, right? And addition-elimination is such that the first step over here, this is step 1, this is your addition step, right? And this step 2 over here is your elimination step, right? So we have these two steps over here, addition and elimination, right? And so that gives us these two products over here, and this is also known as condensation because we have this HCl as a small byproduct, right? So over here in step 1, water, the nucleophile was added, and we got one intermediate, and step 2, we eliminated a small molecule, which is HCl, so addition-elimination, right? So over here we have seen why acyl chlorides undergo hydrolysis the fastest. Now what about the other two? So chloroethane is going to be next in line. The reason is that carbon over here that is partial positive, that will be attracting the nucleophile, is bonded to just one electronegative atom, which is chlorine, and so this partial positive will not be as great as in the acyl chloride, which the carbon is bonded to not one but two electronegative atoms, and so it will not attract the nucleophile that much towards itself. And in the case of chlorobenzene, now there are two reasons why this nucleophile won't be attracted at all, in fact, to this, is because the partial positive of this carbon bonded to the chlorine is going to be delocalized over this entire pi bonding system, right? And the second thing is that because this chlorine carries a lone pair in a p orbital, this carbon is part of a pi bonding system, so this carbon-chlorine bond gets a partial double bond character. And in the hydrolysis, this bond needs to be broken, right, in order for the reaction to proceed. And if this bond becomes stronger, gets a double bond character, so it will not be easy for this reaction to take place. So the ranking is ethanoyl chloride, followed by chloroethane, and then finally we will have chlorobenzene with the slowest rate of hydrolysis. So another reaction that acyl chlorides undergo is esterification, right? Now we have a two-step synthesis over here, and it says the first step produces an acyl chloride. Now the acyl chloride will be produced from the carboxylic acid that we're given with over here, which is propanoic acid. So what we're going to do is we have propanoic acid, CH3, CH2, CO2H. This needs to be converted to CH3, CH2, COCl. So this is basically going to be propanoyl chloride. Now we have three reagents that can do this. So one reagent is simple PCl3, right? PCl3 requires some heating. And basically what it can do is convert 3 moles of propanoic acid to 3 moles of propanoyl chloride. And the other product is going to be phosphorus acid, which is H3PO3. Right. Another possible case is if we were to react propanoic acid with PCl5. Now PCl5 does not require heating, but it will only convert 1 mole of the carboxylic acid into 1 mole of the acyl chloride, and you're going to get 2 other byproducts. One of them is going to be POCl3, and the other is going to be HCl, right? And finally, we have another reagent, which is CH3, CH2, CO2H. This reacts with SOCl2. Again, this is only going to produce 1 mole of the acyl chloride. And you're going to have 2 byproducts. One of them is going to be SO2, and the other is going to be HCl. So you can use either of these reactions, right, to produce the acyl chloride. And now it says we need the reagents and conditions needed for each step of the synthesis. So this was all step 1, right? Now step 2 is once you have produced this acyl chloride, which is propanoyl chloride, this is going to react with phenol, right? Now, how we do this is we have propanoyl chloride. This is going to react with phenol over here. And this is going to give us 2 products. One of them is obviously HCl. This is the byproduct. The other product is going to be the ester, right? So this is going to be C double bond O, single bond O, followed by the benzene ring. So this is going to give us phenyl propanoate, right? So phenyl propanoate is your ester over here. And another proof of acyl chlorides being more reactive than carboxylic acids is that this reaction is not reversible. It does not reach equilibrium. It does go to completion, and we do not need a catalyst for this. So industrially, in order to produce esters like this guy over here, we will actually convert the carboxylic acid into an acyl chloride by step 1, and then in step 2, we will then react it with the alcohol to produce an ester in a reaction that goes to completion without the need of a catalyst. So apart from water and alcohols, acyl chlorides can also react with ammonia or amines. So in compound R, we have both functional groups. We have an acyl chloride over here, and we have an amine over here. Now this over here is a primary amine because the nitrogen is bonded to just 1 alkyl group and 2 hydrogen atoms. If this was just 1 hydrogen and 2 alkyls, that would be secondary. And if there were 3 alkyl groups and no hydrogens, that would be tertiary. Now, step 1 involves just warming this up, right? So when we warm this baby up, what happens is these 2 functional groups will react with each other in an addition-elimination reaction. And what happens is basically an H is eliminated from the amine, and the Cl is eliminated from the acyl chloride group, and we get an amide, right? So if I draw that structure over here, I have C double bond O. This is going to be bonded to nitrogen over here, and the nitrogen is bonded to 1, 2, 3 further carbon atoms apart from the carbon atom in the acyl chloride group. So that's going to be 1, 2, 3, and then the fourth is the one over here. And this first carbon atom that's bonded directly to the NH2 is also bonded to a CH3 over here, so that completes the structure. So we get a cyclic amide over here. This over here is your functional group of an amide, right? We C double bond O, C single bond N, right? And the other product is of course going to be HCl, right? And if you want to check with the formula, right? So we have basically 1, 2, 3, 4, 5 carbon atoms, so that's C5, and we have 1 oxygen, 1 nitrogen in the amide group, and hydrogens will be basically 3 over here and 1 over here, so that's 4, plus 2, that's 6, plus 2, that's 8, and this nitrogen over here is also going to be bonded to 1 hydrogen, so that's 9. So that is the complete formula of C5H9NO. Now this amide over here is going to undergo reduction using LiAlH4. What happens is this oxygen is going to be lost and it's going to bond with 2 hydrogens to form H2O. This carbon over here is going to now bond, instead of with 1 oxygen, it's going to bond with 2 hydrogens. So if I rewrite this over here, that's basically going to be the same structure. Only difference is that the C double bond O is gone, right? Now this over here is basically a secondary amine because the nitrogen functional group, the nitrogen atom is of the amine. It's bonded to 2 carbon atoms. So that's your secondary amine, right? Now the type of reaction in step 1 is condensation or addition-elimination, right? And step 2 is a simple reduction of the amide functional group. Right, now let's talk further about these nitrogen-containing compounds, amines, amides, and further amino acids. So another reaction of amides is the hydrolysis, right? So over here we have an amide linkage in piperine. And basically what happens is you break the carbon-nitrogen single bond over here. This is the breakdown by water, right? So we have the HO part basically bonds to the C double bond over here. The H, on the other hand, bonds to the nitrogen over here. And so that's going to give us 2 new compounds. We're going to get a carboxylic acid over here. And we're going to get an amine over here. Now this nitrogen is bonded to 2 alkyl groups, or actually it's the same cyclic ring, but because it's bonded to 2 carbon atoms, so we'll call this a secondary amine, right? So this is a secondary amine. Now for this, we could use either acid hydrolysis or alkaline hydrolysis. This is a hydrolysis reaction for the amides. And in order to get this carboxylic acid, we want to ensure that we do not have an alkali around, otherwise that will form a salt. So I'm going to use HCl, the acid hydrolysis, so aqueous acid and heat. And piperidine over here is an amine, and it is more basic than ammonia because it has 2 electron donating alkyl groups bonded to the nitrogen with a lone pair, and this lone pair can form bonds with the hydrogen ion, right? So with these electron donating alkyl groups, the lone pair, its charge density goes up, and so it is more attractive to the hydrogen ions, and it can then accept the hydrogen ions, form a dative covalent bond with them. But there's no such electron donating group in ammonia, So I'm just going to write over here that this is more basic because of 2 electron donating alkyl groups bonded to the nitrogen atom with a lone pair. On the other hand, amides with D, amides, are neutral, right? They are not acidic, they're not basic. The reason why is because the carbon-oxygen pi bond has an overlap coming in from the lone pair on the nitrogen atom, right? This p orbital overlaps, so this lone pair over here becomes delocalized, right? So the lone pair is delocalized, and so it is not available to bond with a hydrogen ion, and so amides are neutral, they are not basic. So now we're going to discuss a special amine, which is phenylamine over here. If you have an NH2 bonded to a benzene ring, this is phenylamine with an N. And this production process basically involves these 4 steps. At step 1, you have nitration of benzene. We have already seen this, concentrated HNO3 nitric acid plus H2SO4 catalyst, and a temperature range of 25 to 60 degrees Celsius. This will give us nitrobenzene. Now nitrobenzene has this NO2 that needs to be reduced to this amine over here. So this is a reduction reaction. And for this, the special conditions are tin catalyst plus HCl plus heat. And that's what you're going to do to get phenylamine. Now in step 3, we're going to react it with a mixture of sodium nitrite, which is NaNO2, and HCl at a low temperature of less than 10 degrees Celsius, and that's basically going to convert your amine group into a new functional group, which is going to be called the diazonium ion. So basically you have a nitrogen-nitrogen triple bond, and the nitrogen that's bonded directly to the benzene ring has a positive charge. So this over here is a benzene because of the benzene ring, diazonium because of the 2 nitrogen atoms triple bonded to each other with a positive charge, and this benzene diazonium ion is going to react with the chloride from HCl to give you benzene diazonium chloride. Then what we do in step 4 is just sprinkle a little water on it and make sure that the temperature is greater than 10 degrees Celsius. This benzene diazonium ion is highly unstable, and so what it does, it reacts with H2O, right, or HOH, and the OH goes over here to make phenol, and the H over here reacts with the Cl in benzene diazonium chloride to give you HCl, and the 2 nitrogens in this diazonium part over here, these are just going to give you plain old nitrogen gas, right? So that is the production process of phenol using phenylamine, and in the middle, benzene diazonium chloride. By the way, this benzene diazonium ion is pretty useful in making azo dyes. So one azo dye is methyl orange. It's a famous acid-base indicator, and you have this nitrogen-nitrogen double bond. This, ladies and gentlemen, is your azo group, and we know that azo compounds are organic dyes, right? These are organic compounds which are colored, right? Okay, so for this, what we do is we have the nitro group in our starting compound. You can see that this part over here does not react because it is the same in the start and at the end, so we're not going to be bothered about this. We have the nitro group that is converted into an amine group. First of all, again using the same conditions that we used previously of tin catalyst and hydrochloric acid. So you have tin catalyst plus HCl, hydrochloric acid, plus some heating for the reduction to an amine from the nitro group. Now in step 2, we're going to convert this amine over here into a diazonium ion, right? So we're going to have nitrogen triple bonded to nitrogen with a positive charge that is directly bonded to the benzene ring, and that is bonded to the unreactive SO3 negative Na positive. Right, now this over here is going to react with this arene over here, and this positive charge makes this diazonium ion a pretty good electrophile. So all you need to do is make sure that these two guys react, no special conditions needed, and it's going to give us an electrophilic substitution reaction. And so an H plus will be removed from over here, and this triple bond over here will be converted into this double bond over here, and basically your other product is going to be an H plus that is going to be removed from over here, right? The electrophile that is substituted is going to be H plus, and in this step 2 over here, because we have sodium nitrite and HCl at a temperature of less than 10 degrees Celsius, then the diazonium ion over here is going to be bonded to chloride. So that chloride is going to bond with the hydrogen ion, and that's going to be HCl as your byproduct. So that's how you make an azo organic dye from this nitrobenzene or nitrobenzene derivative. So now on to amino acids. So amino acids are basically compounds that contain carboxylic acid and amine functional groups bonded to the same carbon atom. So over here we have been asked to draw the structure of a dipeptide made up of 2 amino acids. So this is the short form of valine, and this is the short form of lysine. So basically what happens is that the carboxylic acid group of one reacts with the amine group of the other. So if I draw the structure of valine, over here basically this is the general structure of an amino acid. You have a carbon atom that's bonded to the amine, the carboxylic acid group, and a hydrogen. And the fourth thing is an R group. Now this varies from amino acid to amino acid. The rest of this structure remains the same. Now the R group in valine is this fellow over here, so I'm going to draw in that structure. So I have C bonded to H, bonded to let's say NH2 over here. I have CH, CH3, 2, and I have the CO2H. And then I have lysine. All right, now lysine has basically an amine group, again with the carbon, hydrogen, CO2H on the other side, and the R group is pretty long, so I have 1, 2, 3, 4 CH2s. So I'm just going to write this as CH2, 4 NH2, right? Okay, so basically what happens is that the carboxylic acid group of one amino acid loses its OH, and an H is lost from the amine group of the other amino acid, and this is going to give us H2O. And these 2 atoms over here, the carbon and the nitrogen, will bond together, and that will give us an amide, right? So if I draw this again, it's going to be C double bond O and H, and then over here I have the CO2H on the other side that did not take part in this reaction. I'm just going to leave the rest of the structure undrawn, right? This over here is your amide linkage. This is your amide linkage, and in the case of amino acids reacting, the amide gets a new name. We call this a peptide linkage or peptide bond. It's a more biologically oriented term. So peptide linkage between two amino acids. So this is a dipeptide, not because we have two peptide bonds, but because we have two amino acids that make one peptide bond, right? If you had a tripeptide, that would be three amino acids making 3 minus 1 equals 2 peptide bonds. Similarly, a tetrapeptide would have 4 amino acids making 3 peptide bonds. So a separation technique for amino acids, we're going to discuss that right now. It is called electrophoresis. And for electrophoresis to happen, first we need to discuss the existence of amino acids and dipeptides in the form of charged particles. So one such charged particle is called a Zwitter ion, right? And a Zwitter ion is the type of ion that exists out of an amino acid at a pH known as the isoelectric point. So we have been given the isoelectric points of valine and lysine, and basically what happens in electrophoresis is that you dip the electrophoresis paper, shown over here, in a buffer solution of a certain pH, and then you try to pass a current through this. And the buffer in this question is at a pH of 6.0, which is equal to the isoelectric point of valine. So valine in this buffer solution at this pH will exist as a Zwitter ion. Now, what is this monster known as a Zwitter ion? What is this? Now, a Zwitter ion is basically an ion that exists out of an amino acid that has a total charge of 0. It has two charges. One side is positive and the other is negative, and these both cancel out to give an overall charge of 0. So basically what happens is the carboxylic acid group in the amino acid valine is going to give up its hydrogen ion. So it's going to become CO2 negative, and the amine group is going to gain a hydrogen ion and it's going to become NH3 positive, right? So basically from here till here, there was a transfer of an H plus, and so you have a negative side of this ion over here and a positive side over here, but these two cancel out to give you an overall charge of 0. So this is an overall charge of 0 on this Zwitter ion. This is a Zwitter ion. Zwitter literally means 2, so it's going to be 2 charges that cancel out to give you 0. All right, and lysine over here has an isoelectric point of 9.8, but the pH of the buffer is at 6.0. Now, what effect does this have on the nature of the lysine molecule at this pH? Well, thing is that if your isoelectric point is up here at 9.8 and the pH of the buffer is way down here at 6.0, then at this low pH we can assume that there's an excess of hydrogen ions. There's an excess of hydrogen ions. So what we then say is that the basic groups of lysine are going to gain those excess hydrogen ions floating about in the solution at that low pH below the isoelectric point. And so we know that lysine has 2 NH2 groups, 2 basic groups. So we'll have H3N positive over here and NH3 positive over here. The carboxylic acid group is going to stay put. It's not going to lose its hydrogen ion because there's already an excess floating about in the solution, the buffer solution that the electrophoresis paper has been dipped into. So that is the lysine molecule. It is existing actually as a 2+ ion. And in the case of the dipeptide val-lys, what we're going to do is the valine part of this molecule, is basically going to exist in its Zwitter ionic form. So what do I mean by that? Over here, let's say we have our group over here that represents the CH-CH3-2, the side chain of valine. This is the valine part on this side of the peptide bond, and over here we have CO2H. So basically the CO2H will exist as CO2 negative because that is what happens when it is a Zwitter ion, right? It's going to exist as CO2 negative. So that's the valine part. This was the valine part. Now for the lysine part, we're going to have the lysine existing in the form that it exists as when it's on its own in a buffer of pH 6.0, when its isoelectric point is 9.8. The basic groups will have gained H+, so this becomes NH3 positive, this becomes NH3 positive, and so you have two positive charges and one negative charge, and so the overall charge over here then becomes, overall charge is +1, right? All right, so now that we've decided the charges on these ions, we're going to place these spots over here on this electrophoresis paper. Now the mixture was applied in the middle. The Zwitter ion of valine will remain in the middle because it's equally attracted to both sides because of its positive as well as negative charge, and so it'll stay put. Now the competition is between lysine and val-lys. Now lysine has the greater charge, so it will move further towards the negative electrode, and the dipeptide val-lys will be somewhere in the middle, right? In between valine and lysine, because it has half the positive charge and it has a greater MR, so it will move more slowly. So this is the layout of the electrophoresis paper, and once the experiment is completed, once you have passed the current using those electrodes through the electrophoresis paper dipped in buffer solution, then we're going to allow it to dry and then spray on it a staining agent like iodine or ninhydrin to make the spots visible, because amino acids and their dipeptides are colorless. So we want to make sure they're visible. And this is what we're going to get at the end of the day. So let's talk about polymerization. In the A2 syllabus, we focus more on condensation polymerization. And in this question, we have pairs of monomers, and we need to identify the type of polymerization these monomers might undergo. So in this first pair, we have a diol with two alcohol groups and a dicarboxylic acid with two CO2H groups. So the alcohol and the carboxylic acid, we know they react to form an ester. This is going to be a polyester, and the byproduct, which is water, will be condensed out. So this is condensation polymerization. In the second pair, we have, instead of a carboxylic acid group, we have the acyl chloride functional group over here. This will also react with the alcohol group of the other monomer the same way as a carboxylic acid would, and it would form a polyester, and this would be condensation polymerization once again. The only difference is that instead of H2O, we will have HCl as the byproduct. In this third pair over here, we can easily see that we do not have alcohol or carboxylic acid or acyl chloride or amine. These are the functional groups that you need for condensation polymerization, but the only functional group that you need for addition polymerization is the double bond, carbon-carbon double bond, and we can see if we take this monomer as an example, we have this structure over here, and we have in fact a carbon-carbon double bond that is necessary for the addition polymerization. So over here we have two monomers, and both of them contain the alcohol and the carboxylic acid group, right? So when we want to draw the repeat unit of a polymer using both monomers, basically what will happen is the carboxylic acid group of one will react with the alcohol group of the other and vice versa. So let's show how this is going to be. So let's draw the first monomer. I'm going to draw the functional groups on the sides. So I have CH3 and H over here, and I have the alcohol group here, and I have the carboxylic acid group over here. And I have the alcohol group over here of the other monomer. This is going to be CH2. Then I have the carboxylic acid group of the second monomer. So basically what happens is that the OH from the carboxylic acid and the H from the alcohol, these are removed as H2O, which is the byproduct that's condensed out. And so we're going to form an ester linkage between the two monomers. So if I repeat this structure over here, I will get the repeat unit. So it'll be C double bond O, single bond O. Now this C single bond O is what connects the two monomers together. I have C double bond O over here. I have an O over here. So the alcohol lost its H. The carboxylic acid on the right side lost its OH. And the structure is going to repeat. So I'm going to close off the repeat unit with square brackets. Need to show these continuation bonds on either side of the repeat unit, showing us that this will indeed go on. So another type of condensation polymer is the polyamide. So over here we have two monomers. One has the carboxylic acid functional groups. So this is a dicarboxylic acid, and over here we have two amine groups and a hydroxyl group over here as well. But over here they say that we need to form a polyamide. So this OH group is basically just a side chain. It's not going to react. It's not going to take part in the polymerization. So this polyamide is what we need to draw here. Right. So over here we have our benzene ring. We have a COOH, and over here we have the amine group that I am going to display. Then I have the benzene ring, and I have the amine group. And this is going to be the carboxylic acid group on the other side. Now, the OH over here and the H over here will be removed as water. This is the side product, byproduct. And before I forget, I have to have the OH as a side chain that does not react in this case. So the reason why I've drawn a C double bond O over here on the left and an NH single bond on the right is because of the OH being lost from the carboxylic acid and the H being lost from the amine group to form H2O, right? So if I erase all of this and form the amide linkage between these guys, this will make our polyamide. So it's an awfully long bond, but just to save some time, I'm not going to draw them closer together. This is our repeat unit, including residues of both monomers. The residue, remember, is the part of the monomer that's left over after the reaction has taken place. In this case, this is a residue of F. We have basically removed the OH groups from the carboxylic acid functional group, and this over here is the residue of the monomer G, right? So basically a repeat unit includes one residue of each monomer, right? All right, so one thing about condensation polymers is that they are biodegradable, right? Unlike addition polymers. And the type of reaction that takes place for condensation polymers to biodegrade in the presence of bacteria is hydrolysis. It is hydrolysis. It's basically the breakdown by water, and there are two functional groups that can break down like this. One is obviously the ester linkage, and one is the amide linkage, right? So we've already looked at an example of a polyester and a polyamide. In case you were wondering, in our previous example, this over here is the ester linkage. And in this example, we had this guy over here with this very inconveniently long single bond. This guy is your amide linkage. All right, so final topic is optical isomerism. So there's a little bit of a theoretical aspect of optical isomerism that you have to look at A2. You already know that optical isomers basically arise from a chiral center, right? So now over here we have two drugs, ibuprofen and paracetamol, very popular drugs for pain relief. And over here, the first part basically asks us for the functional groups other than the benzene ring. So in ibuprofen, it's going to be the carboxylic acid group over here. And in paracetamol, we have the amide linkage. And we have the hydroxyl group. Now, normally when the OH is bonded directly to the benzene ring, we call this a phenol functional group. So over here, we have carboxylic acid, and over here we have amide and phenol. Right, so ibuprofen contains a chiral center and has two enantiomers. So this enantiomer basically is the technical term for optical isomer that comes up from a chiral center. You have a pair of enantiomers or optical isomers, right? So one similarity and one difference in the physical or chemical properties between the two enantiomers, right? So similarity is that they will all basically take part in the same chemical reactions, right? So one example of a chemical reaction that ibuprofen could take place in is using this carboxylic acid group. So we could say that both react with alkalis to give us salt and water, for example, right? So this is one similarity in the chemical properties. This is one reaction that both undergo, right? The only differences between two enantiomers or optical isomers is that they rotate plane polarized light in different directions, right? So basically, we say that EM radiation exists in multiple planes, right? Planes of oscillations. But if you pass it through a polarizing filter, such as this vertical slit over here, then you're going to get light that oscillates in only one direction. So this is plane polarized light. So one enantiomer is going to rotate light clockwise, and the other will rotate it anti-clockwise, right? So that is the difference, right? So they rotate plane polarized light in opposite directions. And one other difference is that their biological activity. So if one enantiomer is a pain relief drug for ibuprofen, the other might cause some nasty side effects, right? So explain what is meant by a racemic mixture. So normally when we produce drugs like this, both enantiomers are produced at the same time and in a 50-50 ratio, and that is a racemic mixture, right? So this is a mixture that contains equal amounts of both enantiomers, right? So it becomes important to separate the enantiomers into the one that has the desired effect on the body, and the other that might have some nasty side effects. So normally drugs, they are given as pure optical isomer of the isomer or enantiomer that has the desired effect. And racemic mixtures, by the way, if you pass plain polarized light through them, basically the light will not rotate in any direction because you have equal amounts of both enantiomers that have opposite effects on it of rotation that will cancel each other out. All right, we are done finally with the A2 organic chemistry revision video. I tried to make this within 90 minutes, and I hope you benefited from this. And if you like this video, do like, share, and subscribe to Conquer Chemistry for more. And inshallah, I will see you in the next video.